Hello everyone, welcome to another video lecture series on HYSYS and UNISIM simulations, and today we are going to discuss binary VLE data using HYSYS and UNISIM. And a lot of experimental data are available in the literature on binary VLE data, but at the same time during some practical applications we sincerely feel that the actual VLE data is not available, at least for that particular combination. So in those cases this HYSYS and UNISIM may come into your rescue and give you a reasonably accurate VLE data. What happens to a multi-component VLE data, we'll try to discuss that in our future lecture series. But why not we just start directly on how to simulate binary VLE data using HYSYS and UNISIM. These lecture series have been organized by www.Unitoperation.com, and my name is Shekhar Bhattacharjee. So let us quickly go into our simulation systems. The very first problem we are going to discuss is UNISIM create a VLE diagram. So we'll create a XY and TXY diagrams. Of course, other diagrams like PXY diagrams also could be generated very easily for a binary mixture of benzene and toluene at atmospheric pressure. So this is a very standard case, any textbook case of binary VLE data for benzene toluene system at atmospheric pressure. But this is a this is a demo, at least in this case of situation, that how to, for a very basic system, how to use HYSYS and UNISIM to generate or simulate the binary VLE data. So we go to a new case here, and we of course would be using Peng-Robinson equation of state, which is reasonably accurate for benzene and toluene. So we go here, we add the Peng-Robinson equation of state, and then of course we add benzene and toluene in our system. So we add benzene and then we add of course toluene. Okay, so these components have been added, and the Peng-Robinson equation of state has been added. So we directly go to the simulation environment. So here what you do, first you take this mixture here, this icon, and let's add two streams here. One, let's call this as benzene stream, and we put here capital BN, NE, and next we add one more stream here, which is going to be toluene. Okay, and let's call this outlet as mixture. So we are mixing two streams, one benzene, one toluene, and we are getting this one as mixture. Okay. All right. So once we have done that, so what we're going to do is go directly here to the workbook, and first we go for the composition. So for the benzene stream, it is pure benzene, so we just make it 1 and 1. So that's pure benzene, nothing else. So benzene stream is pure benzene, if you can see here. Yeah, this is pure benzene. So, and similarly this is toluene stream, is going to be pure toluene. So we put here toluene, that's pure toluene here. Okay, now we go to this material stream here, and we know we'd be generating this VLE data for 1 atmosphere. So we put here 1 atmosphere here for the benzene stream, and of course this one also has 1 atmosphere for the toluene stream. Okay, and of course the mixture will be coming out as 1 atmosphere. There is absolutely no pressure drop. Next thing what you do, you just put here 0.5. So assume this to be a mixture of saturated liquid and saturated vapor of benzene. So put that at 0.5. Same thing you do for toluene, put at 0.5. That is 50% of it is liquid and 50% of it is vapor. Okay. So once we have done that, so let's go here, and here in this flow rate, mixture flow rate, we put this as 2 kilomole per hour. Okay, so why we have done that, let me quickly explain here what is the strategy for doing this one. What we have here, so we are taking two streams. One stream is your benzene stream and another stream is your toluene stream. So we are mixing them together and we are getting this mixture. Okay, now here we are assuming this stream quality 50% quality 0.5. This toluene stream is also 0.5. okay, and we are saying the stream flow rate is 2 kilomole per hour. Okay, now of course we'd be varying this flow rate from 0 to 2. So correspondingly this toluene stream will be varying between 2 and 0. So that will give me here, if we assume this to be a vessel, that will give me a different mole fraction of benzene and of course of toluene. Mole fraction of toluene is of course going to be 1 minus mole fraction of benzene. So different mole fraction of benzene and toluene, and that will be in equilibrium. So once we get that, then of course once we get these different mixtures, then we can calculate its different properties. So till now what we have done here for the mixture, we have defined this is 2 kilomole per hour, and this is, we said 50% benzene, this is 50% liquid vapor of benzene and 50% liquid, and of course 50% vapor of toluene, and this the entire thing is at 1 atmosphere pressure. So we'll be generating the VLE data. So we'll find out the vapor and the liquid composition here in this chamber here, with varying amounts of benzene going from 0 to 2 and corresponding toluene will be going from 2 to 0. So that will give me different compositions of the liquid and corresponding different compositions of vapor, and will the HYSYS and or the UNISIM will calculate this equilibrium VLE compositions for me, and of course that for temperature, because here we are fixing the pressure. Okay, so that's a strategy. So we go here and let's go to our simulation system. Okay, so once we have done it, so we cross it out, we go to the tools, and then we go to the data book, and here you insert for let's say for the benzene, and for the benzene you will define what is the molar flow. So you go here and we go down all the way, we define what is the molar flow here, and of course once we know the molar flow, then we just say okay, add. Of course that is being added. Okay, next what you do, you go for the mixture, and once you go to for the mixture, you go for temperature. So you add the mixture temperature as one of the variables, and we'll show you why. So here we go for the temperature, we add mixture temperature as variable. So benzene molar flow has been added as variable and mixture temperature has been variable. So next thing what you do for the mixture, again you go for the phase component mole fraction. So here what you go the phase, and you see phase component mole fraction right here. So phase component mole fraction. So which phase? We first choose the liquid phase. So liquid phase mole fraction of what? Benzene. So that is being added. Same thing for phase component mole fraction, you take the vapor phase, and for the same benzene we have added that one. So what we have done so far, so we are going to change the molar flow rate, and correspondingly then we will monitor for the mixture what is the equilibrium temperature and what will be the equilibrium mole fraction of the liquid phase of benzene and equilibrium mole fraction of benzene in the vapor phase. Of course correspondingly we would know about toluene, because this is just a binary mixture. Next what you do, you go for the case studies here, and in case studies you put anything, and of course if you add here, this will come as case study 1. Now you make this molar flow of benzene as your independent variable, and temperature, and of course phase mole fraction of benzene liquid phase, and in the vapor phase you make these as a dependent variable. Once you have done that, then you click on this view. Now you change the benzene flow rate from 0 kilomole per hour to high value of 2 kilomole per hour. Okay, and you can say, you can add a step size of, let's say like to start with 0.2. Okay, so you could have added 0.1, that would have given you many more data points. So we are going to change the benzene fluoride in the feed stream from 0 to 2, and corresponding, of course, toluene would be changing from 2 to 0, so the mixture fluid becomes equal to 2. So once you have set it up, you just start. Okay, so start, you click on start, you don't see much of a change, but once you click on the results, you can see these are the results. Okay, that really doesn't show you much. So what you go, you click on this table. So in the table, of course, that shows you all the data what has been generated. So see, for as the molar fluid of benzene changes from 0 to 2 at a step size of 0.2 here, you can see the corresponding, of course, toluene fluoride changes from 2 to 0 all the way here. You see the mixture temperature. This is, of course, pure toluene. That's why 110.3 degrees Celsius, which is a normal boiling point of toluene, and of course this is a normal boiling point of benzene, pure benzene. And this is just the intermediate mixtures of different compositions, different proportions of benzene and toluene. So you select all these, then you go here and you click on the edit and you say copy with labels. So once you've done that, then you go to then you click on Excel. So you open your Excel sheet. Once you have clicked your Excel sheet here, so we will show here. So here, let's say you just go paste. Okay, so once you have done the paste, you see these are all the data which have been generated by the HYSYS or the UNISIM, and we have taken those data and exported to Excel. Now we are going to create the TXY diagram and the XY diagram. So how do you do that? That's kind of like easy. First you choose these two data here, that means the temperature and the mole fraction of benzene in the liquid phase, and then you go for the insert, and then you go for the different types of charts. So go for the scattered chart. I'm just choosing this one. So it is showing this one. The problem is it has not really properly collected which one what will be the x and y values. So what you do, you click on the layout and you click on you click on the design, and you click on this design here and you click on select data. Once you select, see it has selected the series 1, but you have to edit it. How do you edit it? So first let's call this as my TX values, and you choose the x values. X values, of course, is going to be your mole fraction in the liquid phase. So these are my x values. Okay, you choose this one and hit enter. And for the y values, what you do, you choose temperature. So this is my temperature. So because I'm trying to create the TX diagram. Okay, so this is what it is. So you click on here OK, and you see that automatically comes in here. Next, of course, you have to do the TY diagram. So you add another series here. So what you do, let's call this as TY. And what are the x values? X values would be the mole fraction of benzene in the vapor phase here, and so that is taken. And what would be the y values? Y values again would be the same, temperature, because it's a TXY diagram. So you click on that. So you see automatically, you see this kind of like TXY diagram has come in. You hit on OK, and you hit on OK. All right. Now it needs a little bit of cosmetic changes. So what needs to be done here? First, what you do, you click on this x-axis label here, and you say format x-axis, and you of course change this minimum, maximum, and the major units. So maximum cannot be more than 1.0, so we put 10, and let's see, this is 0.2, that is okay. So we close this one. And similarly for y1, as you can see, if we really start from like 70 at the bottom and all the way up to 120, that should really do it. So we click on this one and you say format x-axis, and you say, click on these three, and we put here 70 as my minimum, and 120 is okay, and this 20, instead of 20 you can make it 10 as a major units. So once that is done, that is pretty much okay. Now what you do, you just change the look a little bit. So you go for the grid lines, you say primary horizontal grid lines, so I'm going the major grid lines, and for vertical grid lines I'm giving the major grid lines. Okay, that's how it looks like. So it's going from 0 to 1, 0 to 1, and of course that's pretty much done. So in terms of axis title, primary horizontal axis title would be title below x-axis, so this should be x comma y, and that's this. And for the y-axis, vertical axis, it should be rotated title. Let's put that as t. So we have this TXY diagram. Then you can make some cosmetic changes on this one also. So you click on this one, so all the data would be selected here. So right click and it will be format data series, and you go for the marker option. I go for the built-in marker option, and I go for, let's say, this nice one here, and change the size a little bit. And then we go to marker fill, we put the solid fill, and we cross and make it black here. And then we go for the line color, make a solid line, and let's make it black color here. And line style, I just make it a little thinner. You can make whatever you want. So that's basically it. So that's my TY diagram. And of course the same thing here, we click on that and say format data series, and you go for the marker option. So let's choose a different type of marker. You go for the built-in, and you go for a different type of marker. It's use the size a little bit, go for the marker fill, you go for the solid fill and make it black. Okay, and line color, I prefer the black one, so go for the black. And line style, as I said, again we change this one to 1 point. That should do it. So basically this is my TXY diagram. As you can see, this has come out very nicely. So let's keep it right here. Okay, so that's basically it. Now let's create the XY diagram. For creating the XY diagram, what you have to do, you have to have a diagonal. So I just write here diagonal here, and that's the way I do it, but you can do it in a different way also. There are other ways of doing it. And so what I do, I just take this one and copy this one and press paste exactly the same values here. So that will give me the diagonal. Okay, so now what I do, I just choose this as my x, this temperature. No, this is my x and y values I have to put. So this is my xy values, and I go for the insert, and I go for the scatter diagram. And now what do I do? You go for select data, and so series 1 has been selected. You edit this one, so let's call this is my xy data here. Okay, and the series x values would be of course liquid phase values here. So this is my x values, and of course y values here would be this would be my y values. It has already been selected, but that's what I do. So that's pretty much it. Okay, now I add another series here, and here what I do, this is my diagonal. So here I choose the same x value here, which is the liquid phase, this one, and for the y values I choose the diagonal, which is exactly the same values. So that gives me the diagonal values. Now once that is done, then what we do, you go for so this is okay, and now I go for the layout. So here you come here, and just like the previous one, here I format the x-axis, and of course we go here and I choose this is going to be 0, this is going to be 0, and this is going to be, let's say, 0.1 unit, and same thing for this one. So here I go for between 0 and 1. So I click on these, I go for 0, and I go for 1 here, 1.0, and this is going to be of course 0.1. Okay, and that pretty much takes care of it. Now you go for the grid lines. under the layout, so you go for the grid lines, you go primary major grid lines. You could have given minor grid lines too, but anyway I don't need that. So you've got the grid lines here, and now what you do, you just the previous one, you just format the data series. Just the previous one, I go for the marker option, I go for the built-in, I go for this bullet here, and marker fill, I go for the black color. So black color, and line color, of course, is I want solid line, so that's black, and line style, I again go for 1 point. That, but you could choose anything you want to. And same thing with the diagonal here. Choose the diagonal, format data series, and here go for the marker options, go for built-in. Here you go, and it chooses cross one, and the marker field, I go for the black color here, and line color, solid line, again I go for the black color here, and the line style, again I go for 1.0. So that's basically it. So, and you can just put XY title, horizontal axis title below axis would be X, and of course for the axis title, vertical axis I want the rotator, and let's put that as Y. So basically, so this is my XY diagram. So that's the way you do it. So what we have created here, you can put a chart title too if you really want to. Above the chart, you can just say benzene dash toluene, okay, and that pretty much creates this one. So that's the way you do it. So let's go. So I've taken the same thing and put in my this one here. As you can see, that's the way I have done this TXY diagram. This is my temperature. So this is my XY diagram, and here's T, and this is my XY diagram. So this is my TXY diagram, and of course this is the typical lens, and of course any horizontal line would be your tie lines. We already know that. And of course this is 110 degrees Celsius, that's the normal boiling point of toluene, and the normal boiling point of benzene, and this is my diagonal line. So these are very standard textbook things, but just to show you how to create a binary VLE data for a simple system. So now let's go for a little bit odd another system, which is the same thing, just how do I create for the binary VLE data for diisopropyl ether and 2-propanol. I'll follow exactly the same thing. So this time I'll go a little bit of quickly. So what we're going to do here, cross this one, just go for a new system here. So let's go for a new case here, and just here what we have here, this is slightly different. We'll do it for atmospheric pressure, but we use Wilson equation of state for the liquid phase activity coefficient, and ideal gas equation of state for the vapor phase property prediction. So that's what we're going to do. This equation of state would be using for prediction of the activity coefficients for the liquid phase. So this diisopropyl ether and 2-propanol, and of course atmospheric pressure, assuming ideal gas equation of state for the vapor phase, it's not going to be too far from reality. So we are going here. So for the fluid package, what we do in this case, we don't choose Peng-Robinson. Now we're going to go for Wilson equation of state, and here for the vapor model, here you can see you could have chosen Peng-Robinson, SRK, so many other RK, Deadly Kwong, etc. But let's say we are just satisfied with ideal gas equation of state. Another thing, you just make sure that so here parameters, let's see here, setup. Okay, this has been chosen. First you have to do the components here. We have diisopropyl ether, which is this one, so I'm going to add that, and then we have to add 2-propanol, so 2-PRO, this is right here, 2-propanol. Okay, so I have added that compound. So I have added these two compounds, and I have added Wilson equation state for the liquid phase activity coefficients and ideal gas equation of state for the vapor phase activity coefficient. I want to show you that you have to make sure that this binary interaction parameter values are also given here, so that kind of helps. Okay, so with that, so we go to simulation environment. Rest of the things are very easy. We just go here, and of course, as I said, I take a mixture here, and in the mixture I just give first stream is, let's call this as ether, and the second stream, let's call this as 2-propanol. Just call it as propanol. I'm quickly showing that propanol, and let's call this as a mixture. Okay, all right. So with that, we go here, and what we can do, we go here in the workbook, and as I say, for the first we choose a composition. For the ether phase, we say this is pure ether, and click on that. And for the propanol phase, we say this is pure propanol, so hit enter, and so this is pure ether, pure propanol mixture. Okay, and the material stream, first you have to define, say this is my atmospheric pressure for both of them, so we go for atmospheric pressure here. This is atmosphere, and the same thing here, I go for atmospheric pressure here, so we go here. All right, and then of course we say make it 50%, and the quality is 50%, so 50% liquid, 50% vapor, and the same thing here, 0.5 liquid and vapor. And of course this is going to be at the saturation temperature for the ether, and of course because it's a liquid vapor mixture, saturated mixture of liquid and vapor, so they are going to be at the saturation temperature, which for ether is 68.49 and for the propanol is 82.25. And finally we said this is, we're going to make this as 2 kilomole per hour for the mixture, and would be using the data book, would be changing the flow rate of ether between 0 and 2. That's the strategy. So once we done that, so we go for the tools, and we hit the data book here, and we say insert, and in the insert first we choose ether, and we go all the way down to the molar flow, so we choose the molar flow, and we have to add that. So that has been added, ether molar flow has been added, which we said would be varying between 0 and 2. The next one is for the mixture, so we're going to take the result, find a mixture, we choose its temperature here, so we go for here its temperature, we go for the temperature here, and so we add that as one of the is going to be one of the dependent variables. Again, for the mixture we go for the phase component mole fraction, so phase component mole fraction, and we have to choose for the, let's say, liquid phase of ether, so we choose that, and similarly phase component mole fraction of vapor phase of the same thing, ether, so that's going to be added. So these 4 parameters have been added. What is the ether molar flow rate, and for the mixture temperature, and mole fraction of ether in the liquid phase, mole fraction of ether in the vapor phase. So once you've done that, you kind of like drag it, and you go for the case studies, so you just put anything here and you add, so this becomes case study 1, and then you go for molar flow rate would be making the independent variable, which we will change, and these of course would be dependent upon the changing of the independent variable, so we keep this as dependent variable. What are the dependent variables? Depends on temperature, then we have liquid phase mole fraction of the ether and the vapor phase mole fraction of ether. So once you have done that, go for the view, and you change the low bound between 0 kilomole per hour to 2 kilomole per hour, as we have discussed before, and that's the step size is 0.2. You could have made any other values, you can make it 0.1, 0.05, whatever. Smaller the step size, of course larger will be the number of data points. So as you change the molar flow rate of ether between 0 and 2, correspondingly the molar flow rate of propanol will be changing between 2 and 0. That's the idea, and correspondingly the mole fraction will be changing. So for that, each mole fraction we'll see what are the temperatures, equilibrium temperatures, and what will be the corresponding equilibrium liquid and vapor phase composition. So once we have set it up, we just say click start, and that's done, and you see the results. Just as usual, go for the table, and now what we do, we just click drag it, and you choose all the values here, and then you go for the edit, and say copy with labels. Just like the previous one, go for a new new one. I'm going for the new one, and you say create blank folder, create. So I go for a new one, and again just paste. The moment you paste it, all the values are pasted here. Okay, so it's the same thing, and I'll just quickly show you how to do that. So basically, first we have to choose this liquid phase at this one, temperature, and the liquid phase ether. So we say insert, and we go for the scatter and go for this one. And now once we have done it, so we choose select data, and this is for the series one. We edit this one, and we call this, let's say, as tx data points, and for the x values we choose the liquid phase mole fraction of ether, and for the vapor phase we choose the temperature. And so that's what it is. And so okay, and what we do next, we have to add one more data series, which is going to be by ty. Okay, for the ty, the x values is going to be, of course, the vapor phase mole fraction of ether, and the dependent variable, of course, is going to be my temperature here. Okay, so that's basically it. And as you can see, at certain point it's forming azeotrope, so that we will clearly see that. So as we said quickly, we just change this one, format the x series, and we just change these values to 0.0. so I just change to 0, and let's say this time we make the major subdivision at 0.1. so we got that. And here the temperature, let's vary between 60 and 90. That should do it. So we clearly go here and we format the x series, and we change the values between 60 and 90, and you can make it, let's say, 5 as your this one. Okay, so once we have done that, so you see it's clearly forming an azeotrope right here, which has actually experimentally been proven. So next we go on the layout, and we for the grid primary horizontal major grid lines, and similarly we go for the prime vertical, we go for the major grid lines. Okay, so and we clearly go here and format the data series just the one before. We go for the marker options, we go for the built-in, and we go here and change these values. Then of course we go for the marker fill, change the solid, and we it's all black, so we go for the line color, and we go for black, and line style we make it 1. Okay, and so that pretty much done for this one. And the same thing for this one, we go here, change this one to marker fill. I'm not going to really go for details on this one, I'll quickly do it. Marker options, built-in, we go here, and let's say take this one and change this value here, and marker fill, make it black, solid fill black. Okay, and line color, so okay, and line style we change this one to 1. Okay, so basically that's what it shows. Okay, so once we draw the XY diagram, that will be more clear. So why not we just, as we say, we put the diagonal here, diagonal, and if you put the diagonal here, take this value here and make a copy and paste exactly the same value in the diagonal here, paste. And now what you're going to do, you just choose the XY values clearly and insert, so scatter diagram here, and as you can see, this is a nice one. So this is coming, so it's right around here, it will form the azeotrope. And of course you go for design, select data, and this is the one, and edit, and what you do, choose the value of x, which is right here. Okay, and for the y, it is already has chosen this one, so but again let me do it. Okay, and so this is done. Now we have to add one more series here. This series of course would be x values would be the same as this liquid one, and y value would be of course for the diagonal. We'll choose this diagonal values here, which is the same, exactly the same, right? And clearly let's make it format the data series. So this is okay. Format the data series here. Okay, format axis here. So we go for all these three. So we make it 0, make it 1.0, and let's make it 0.1. Okay, and similarly for this one, we make it format x-axis. So we go here and 0, so this should be 1.0 because the mole fraction cannot be more than 1, and let's make it 0.1, and that should do it. Okay, and change these data series here, format data series, which you have done. Marker options built in, I'm going here and we put here, and then we go for marker fill, solid fill, and back, and then we go for the line color, solid line, and here, and the line style of course is going to be here. So that's my line style, and here we go this one from a data series again. We go for the marker options built in, and we go for this one, and we go for the marker fill, we go for solid, and we go here black, and that makes it this one. Line color, solid line, and black, and line style, we reduce this one. Okay, so that pretty much does it. So as you can see here, right here, this is forming the azeotrope current right here. Okay, so this is my x. So in the layout, as you can put that, the axis titles, horizontal axis title below the axis would be x, and of course axis title, vertical axis title would be of course rotated would be y. So basically that's what it is. So exactly, so actual experimentally it has been observed pretty much these values has been observed. Now also that the advantage of this one is that if you want to change the equation of state, instead of Wilson, let's say if you think that some of the equation of state might be more useful, so you can just change to any other value. So you go here setup, and you can change to say uniquark. You can do that just to make sure that the binary coefficients are available. So yes, if it's available, so you can get it all together different set of data. So you can try different equation of state both for the liquid phase and the vapor phase, and you can generate different sorts of data. So that's the way you do it. You generate the binary VLE data using HYSYS and UNISIM in such a wonderful way, and in our future video lectures I'll show you how to do that for ternary system or either for multi-component systems. So I'll see you in my next video lecture series. Thank you.